Today we're going to take a look at the binomial theorem and the return of an old friend. So as a quick review to the combinations we've been working on, go ahead and calculate the answers for the following combination problems. You can pause the video, get your 5 answers, and then come back when you're ready. So here are those 5 answers. Awesome. I'm just going to store them here in this little table for future reference. Now, because there's nothing more fun than multiplying binomials, okay, we're going to multiply out x plus 1 all to the 4th power. And I chose plus 1 because I didn't feel like doing a whole lot of complicated math. So here we go. I'm going to start with doing x plus 1 times x plus 1. So that's 2 of the x plus 1s that I'm going to be multiplying together. I then take the answer to that problem and I multiply it with the third x plus 1. And then I take the answer from that problem and multiply it with the fourth x plus 1. And in the end, I get x to the fourth plus 4x to the third plus 6x squared plus 4x plus 1. Do you see anything? Because I don't know, there's something about that answer's numbers that seem to be ringing a bell, like a weird deja vu kind of thing. Oh, not deja vu at all. The coefficients of my final answer are the exact same numbers of those first 5 calculations. Hold up. How is it that answers to combination questions are showing up as coefficients in a polynomial problem? Isn't that just a little bit weird? If you ponder, it's probably not that weird, because if I'm multiplying binomials, I'm multiplying a lot of the same thing, the x plus 1, over and over and over. So I am going to be mixing up my x cubes, squareds, x's in different combinations. So it does kind of make sense, but it's still a little creepy. Now, you might be thinking, yeah, but it just feels like that sequence of coefficients is somehow more familiar than just I did the answers at the start. There's something about it that's triggering this deja vu from probably months ago. It's our friend, Pascal's triangle. Take a look at Pascal's triangle and see if you spot anything familiar. So we have Pascal's triangle. All right, now this is getting weird. Combination answers, which is one whole thing of math, binomials, which is another whole thing of math, and then this Pascal's triangle, which we learned is just a quick adding and getting sums and everything, so it's just a pattern, and they all somehow have the same sequence of numbers? This leads us to the binomial theorem. There's a really technical definition that involves symbols and n's and r's and all whatnots and c's. I'm just going to go sort of English. If you want to multiply powers of a binomial, there are patterns. There's a descending pattern, there's an ascending pattern, and it's the same pattern every time. There are also constant scale factors associated with each power. And by constant, not only do I mean no variable, just a number, but always the same. Every power has its associated scale factors, and they are always the same. You can get those scale factors either by doing combinations, which is NCR, n being the power of the binomial in question, and r is what position in the final answer that term will be sitting. Or you can just steal them right off of the nth row of Pascal's triangle, and then they're already in order. Now, this might be all you need, and you're just like, hey, I'm ready to go. Most people probably need to see this worked out. So let's do it. We're going to do x plus 3 all to the 5th power. Now, to keep things organized, I like to put this into a table form. So to do the table form, I need to have one more column than the original power. So in this case, it was a 5th power. I need 6 columns. There will always be 4 rows. The first row is where I'm going to put the pattern associated with the term 1. The second row is going to be the pattern associated with term 2. The third row is going to be where the scale factors go. And the bottom row is going to be where my final answer shows up. So in this problem, term 1 is x. It's the first term in that binomial. Term 2 is this positive 3. It's the second term of this binomial two-term polynomial. So I am going to start with term 1. Since it's a fifth power, I know the final answer is going to have an x to the fifth at the front. So I'm going to start with x to the fifth. And then this row is my descending pattern. It's going to go fifth, fourth, third, second, first, gone. And there it is. Now I'm going to do the same thing with the 3, only in reverse. The 3 is going to be the ascending pattern. And I'm going to do it the same way I did x, only backwards. None, 1, 2, 3, 4, 5. And there are my powers of 3. Now I need to go steal some scale factors. Since that's a 5, I need the fifth row of Pascal's triangle, or I need to do 5C0, 5C1, 5C2, 5C3, 5C4, 5C5. Pascal's is quicker, so I'm just going to steal that row. And all I have to do now is multiply down the columns. That's it. Just multiply everything in a column and see what the answer comes out to be. Don't forget you do your exponents first. And there are the final answers. Which is the final answer? Now, if you really would like to multiply x plus 3 to the fifth power out the long way, using lots of generic rectangles and things like that, you're welcome to do it. You will get the same answer. Okay, let me try this again. If you're feeling pretty confident, you could try this one by yourself and then come back and see how you do. If not, you can certainly just watch this one in action. So, term 1 is x. Term 2 is negative 2. It's a sixth power, so we're going to use the sixth row of Pascal. So descend my x's, 6, 5, 4, 3, 2, 1, none. Ascend my negative 2's, none, 1, 2, 3, 4, 5, 6. You notice the negatives in parentheses. Super important. I'm doing negative 2 to a power, not negative 2 to the power, which would be the opposite of 2 to the power. So be careful about that one. All right, there's my row 6, went and stole it. All I have to do now is just the math. Multiply down the columns. If you have a calculator, it makes it really easy. Just be sure to put that parentheses around the negative 2. And you'll notice every odd power of 2 comes out as a negative answer, as it should. And so there's the final polynomial. Cool. So we notice on this one, there was something else in front of the 2, this negative. So it had to go in here with the power. All right. Then how about you guys try this one? See if you can set it up and get to a final answer. Pause and come back when you're done. Welcome back. There it is. So this time, just like we did with the negative 2, there was a 4 in front of the x. So the 4 had to travel down with the x. So then in our first term, I end up with 4x all to the third. That's 64x to the third. And then I have a 16 times a negative 5 times a 3, and then a 4 times a 25 times a 3, and then a negative 5 to the third power. And so there it is, 64x cubed minus 240x squared plus 300x minus 125. Awesome, right? But wait, there's more. Pascal has not even begun to tell us all of the cool things that it knows how to do and all the cool little patterns that it's got buried in its somewhat simplistic looking structure. Remember how we calculated those combinations problems back at the beginning? So 4C0 would be having 4 items but taking none of them. There's actually one way to do that, right? You just don't. Or 4 items, choosing one at a time. Well, if you take one at a time and there are 4 things, there are 4 ways to do that. 4 items, taking 2 at a time, 4 taking 3 at a time, and then 4 taking 4 at a time. Well, that means you're taking them all. There's just one way to do it. Take them all. But those numbers are row 4 of Pascal. Hold up. So not only are those the binomial scale factors, but now the answers to every combination problem are just sitting right there in that triangle? You betcha. Now, that might seem creepy to you, might be cool. I find it cool. That is what Pascal's triangle is just so good for. You can find answers to combinations on here. So building a Pascal's triangle, which is easy enough to do, can give you a cheat sheet for every combination problem. And there's nobody on like a test who can stop you from writing down a Pascal's triangle. So even if you didn't have a calculator and you needed to do some combination problems, just build a Pascal's triangle and you're all set to go. Every answer is right there. You just look it up and copy. Let's see how this works. So you decide it's time to have an ice cream sundae party with your family. You've been cooped up for a long time and the only solution to that is ice cream, clearly. So you head to the grocery store and you bring back vanilla, chocolate, and cookie dough ice cream, of course. You buy chocolate syrup, caramel sauce, sprinkles, some Oreos to crush up into cookie crumbs, some whipped cream, some mini chocolate chips, and the little can of chopped up sundae nuts. And then because what's an ice cream sundae party without something cool to hold the ice cream? You get some sugar cones, that's the crunchy pointy ones, some cake cones, those are the ones people like to bake cupcakes in, and then waffle bowls. So let's do a quick inventory here. How many ice cream flavors do we have to pick from? 3. How many toppings do we get? There are 7. And how many vessels or containers do we have to choose from to hold our ice cream? 3. All right, so let's say you are a load up my sundae kind of person, and you plan to take 5 of those 7 toppings and pile them on. How many different ways could you do it? If you think you know what the answer is going to be, pause, calculate it real quick, and come right back. Well, that's 7C5. So on my calculator, I put in 7C5, I got 21. But wait a second, hold up. 7C5? I wonder. In that last coefficient thing, I was doing a 4th power, and I was doing 4 items choosing at a time, and it was the 4th row of Pascal. Wonder what happened if I go to row 7, position 5. Row 7, position 0, 1, 2, 3, 4, 5. But that's the same answer. Oh, interesting. Okay, since that was so much fun, what if you are a little bit more of a minimalist? So you like more than 1 topping, but 5 is too many. Let's go for 3 at a time. See if you can use Pascal's triangle to get the answer now. Did you get 35? Row 7, toppings starting with position 0, 1, 2, taking 3 at a time. Oh, okay. What about the ice cream? Like, let's say this is such a crazy great party that you decide you're going to have 2 different flavors of ice cream in the bowl. You're not even going to stick to just one. You're going to go for 2 ice cream flavors. So how many different combinations could you make of the ice cream that you bought? Well, if you said 3, choosing 2, and so you went to row 3 and position 2, and you found that there are 3 ways of doing it, nicely done. Okay, so now let's do a little basic counting principle. Let's say that now you're going to choose 1 vessel, because, it'd be weird to have a waffle bowl and a sugar cone. So 1 vessel, 2 flavors of ice cream, and 5 toppings. How many different sundaes could you make? Go ahead and pause, see if you can figure it out. If you had 3 times 3 times 21, you are right. 3 vessels to pick from, 3 ways you could combine the ice cream, and 21 ways you can combine the toppings. So 189 different sundaes. That means you could eat a different ice cream sundae every other day, and it would take you a little over a year to try every possible combination. That might be a good goal in life. Okay, Now, what if somebody said, no, I actually just want to know. You put 7 toppings out on that kitchen table. How many different ways could I combine them? And that's any number of toppings. So it's someone who wants none, the purist. Just give me my ice cream and go away. And then the person who says, I don't care what you have on that table, put it all on. I want the kitchen sink sundae. Everything. You want all the possibilities, every possible way of combining toppings. That, my friends, is a series. And if I whipped out all my fancy math notation, I could pull out sigma and a bunch of other cool things. But really, let's just think about it. What I need to do is just add up row 7. Because each position represents a number of toppings I'm taking. So this first one is the number of ways I can have 7 toppings but take none of them. There's one way. Don't take any. This represents 7 toppings taken one at a time. There are 7 ways I could do that. This is 7 toppings taken 2 at a time, taken 3. So if I just add up the whole row, that's all the different ways I could combine all the different toppings. That means that with 7 toppings, there are 128 different toppings combinations. You might want to try something really interesting. Think about if you were to add up all the possibilities if you started with 6 toppings or 5 toppings. So basically, add up each row of Pascal's triangle. If you want to see something really interesting and a super fast shortcut, try doing that a little later. Just add up each row of Pascal's triangle and see what kind of numbers you get. So now, let's say you choose 1 vessel, 2 ice cream flavors, and any number of toppings. So that's 3 different vessels to choose from, 3 ways to combine the ice cream, and now 128 ways to mess with the toppings. That is 1,152 different sundaes. That is a very cool thing. Very cool. So, in conclusion, we need to all go eat ice cream. Yep, absolutely. So just for visual sake, there's your waffle bowl, there's your sugar cone, kind of waffle cone, there's your cake cup, and there's just a good old-fashioned bowl. But we went with edible vessels. No, seriously. In conclusion, Pascal's triangle is just basically magical. Each row represents scale factors for a power of a binomial, and each row contains all the answers to combination problems. And so the only thing left to do is to test out the whole ice cream topping theory ourselves, right? In the interest of fully understanding the mathematics, of course. Make sure to go back and try that little secret trick with the rows of Pascal, and enjoy some ice cream.